Good day, grade 12. We're here back for another day of physical sciences, and we're going to continue where we left off last week. We are going to focus on rates of reactions. Now, to quickly recap on what we did last week we focused on collision theory, okay? And then we investigated the factors that influence the rate of a reaction, okay? And those factors were concentration, okay? And we have temperature, we have pressure, okay? We have nature of reactant, and then we have catalyst, okay, suitable catalyst, right? Then we talked about activation energy, okay, and activated complex. Okay, so what I did last week, I defined collision theory. I then explained why the rate of reaction is dependent on these things, and then something else that you have to know is to explain why these affect the rate of reaction according to collision theory. So we have to put this in terms of collision theory, and then I actually explained the difference between activation energy, and activated complex. So if you want to know more about these, just go back to the lecture that I did last week. Alright. Okay, so what are we going to do today? Today we are going to talk more about catalysts, okay? Catalysts. And then we are going to talk about energy graphs. Okay, energy graphs. Well, we're going to do this one first and then that one after that, okay? Because I first want to explain energy graphs and then how a catalyst then changes an energy graph, okay? Alright, let's get straight into that. Alright. Okay, so in a chemical reaction, you have reactants A plus B, which will give you the product C. So what happens is A and B react together and then they form C. Now, as we said again, certain reactions happen at certain temperatures, okay? Temperatures. Remember, temperature is one of the factors that influences the rate of a reaction. Okay? So, let's take this reaction. This is a different reaction. C plus D will give you E. Okay? Let's say this has a certain activation energy. Let's say of 5 degrees Celsius. Or let's make it 25. And then this one is 27 degrees Celsius. Okay? So, what does that mean? Again, I'll redefine activation energy. Activation energy. Okay. Activation energy is the minimum amount of energy needed for a reaction to occur, right? So it means if two reactions reactants are forming at a temperature below the activation energy temperature, let's say 24, this reaction will not happen, okay? And if this one also happens at a lower temperature than this reaction will not happen. So a certain amount of energy is needed to start certain reactions, okay? Right, so we got that out of the way. Now we have an energy graph that explains this distribution of energy. This is called the Boltzmann distribution Boltzmann distribution curve. Okay? This explains the distribution of energy within a chemical reaction. Okay, so what does the graph look like? Let's draw it quickly. So here we have number of particles. Okay? And here we have energy. Alright? Energy, which is temperature. Right? Which is basically the average kinetic energy. Okay? Okay, this is what that is. Okay? We have a first curve that goes like that, and then we have another curve that goes like that. Okay, let me draw that properly. That goes like this. Okay, good. So this is T1, temperature 1. This is T2, temperature 2. Okay? Now, T2, okay, is indeed greater than T1. So what that basically means is that this part there has higher temperature than that part there. Okay? And the area under the curve, so we have curve 1 and we have curve 2. So the area under the curve is basically the amount of particles. So the amount of particles in a reaction stays the same. So you have a reaction, again, A plus B takes you to C. So the amount of particles don't change. So temperature doesn't change the amount of particles in a reaction. Okay? This has lower energy. So T1 is low temperature. Temp, let's write it like that. 2. So it says high temp. Okay? Right. And then we have a marker there. Okay, let's have it here. Let's just increase that curve just a bit. There we go. And then let's have a mark there. And let's call this point E1. Okay? And let's shade it in, shade it in, shade it in, shade it in. Okay, so what is this shading? This shading we can actually call activation energy. Right? So this is the activation energy. So this reaction will happen at this temperature. Now remember, these are not two different reactions. The first curve and the second curve is the same reaction. So T1 and T2 are the same chemical reaction. The only difference is that T1, the reaction is happening at a lower temperature, and T2, the reaction is happening at a higher temperature. Okay? So, and then we have a marked point, which is called E1. Now, E1 is the activation energy. Remember, activation energy is the minimum amount of energy required for a chemical reaction to occur. Right, so only at this point and beyond will the reaction start to occur. Now notice something. at T1, there's only a small part that actually falls within E1 and beyond, right? It's at a lower temperature. At T2, you'll see that most of the curve falls within this area. So what does that mean? It means at a higher temperature, there is a higher rate of reaction, right? So there's a higher rate of reaction at T2 because most of that curve falls beyond E1, and at T1, most of that falls behind E1. So it means here at E2, higher rate of reaction for this particular reaction. Okay? So that's what the Boltzmann distribution curve is. It is explaining the temperature of the same chemical reaction and then tells us why one reaction will have a higher rate of reaction than the other reactions. The same reaction, just at different temperatures. Okay? So this is what we call the Boltzmann distribution curve. And we're explaining this in terms of temperature. Okay? So keep in mind temperature, and remember temperature is the average kinetic energy. That's why I wrote this here. Sometimes they'll write here energy, right? And sometimes they won't write energy, they'll write average kinetic energy. Okay? It's the same thing. That's why I wrote both of them. It's exactly the same thing. Okay? Boltzmann distribution curve explains rates of reactions for temperature. Okay. Let's move to another energy graph. Now this energy graph will teach us about two kinds of reactions. Okay? The first reaction is exothermic. The second reaction is endothermic. Okay? Now these energy graphs are going to explain the difference between the two. What's the difference between an exothermic reaction and what's the difference between an endothermic reaction? Okay, let's begin. Let's have a graph for an exothermic reaction, and let's have a graph for an endothermic reaction. Okay. Alright. So we'll draw the graph like this. Okay. Let me draw it better. We'll draw it like that. There we go. And here we will draw it like this. Okay? Then what goes on here? Potential energy. So basically it's the energy of the reaction. Potential energy. Okay. Alright, and then here what we have the reactants. Okay? Let's write that better. We have reactants, or they'll write reagents, it's the same thing. And here we have products. Okay? Products. So this is a chemical, so this represents an energy curve of a chemical reaction that has went from reactants to products. So this chemical reaction has happened. Okay? Okay, what else? We have this here, which is the activation energy. activation energy. Okay? And this point here, specifically at that point, here at this point we have the activated complex. Okay. Now remember, there's a difference between activation energy and activated complex. Right. Remember, activation energy is the minimum amount of energy required for chemical reaction to initiate, to start. Okay? Right. Now, what is activated complex? Let's write it down. Activated complex. Good. Activated complex is a temporary, unstable, high energy composition of atoms that represent the transition state between reactants and products. Okay? That's activated complex. Again, temporary, unstable, high energy composition of atoms that represents a transition between reactants and products. Okay? So it's right in between there. Remember what collision theory said? Again, you can go back to last week's video if you didn't watch the lesson on collision theory. So collision theory basically says, in short summary, in order for atoms, particles to react and form a chemical bond, they need to collide, but not only collide at the right energies, right? Okay, so here we have reactants, right? Okay, we have it's a particular compound or element or atom or particle, however you want to put it. And then we have B, right? And what they need to do is form C. Okay? Whatever the new composition is going to be. But in between that point, which is this point, right, there needs to be a reaction that happens. Now what collision theory says, it says that these need to collide. These particles have to collide. So particles from A need to collide. Boom. Collision. Need to collide with particles from B and have an effective collision. Effective collision, remember, is collision that happens at the activation energy, right? So they will collide. They are in very high energy. They are colliding, very unstable and temporary. And then after the collision, then the product forms. Okay? So that's what activated complex is actually. It's this state. So here you have reactants, and then suddenly you have products. That's what the reaction would say. But in between there, they need to actually collide and react. And that point of collision is exactly the activated complex. Okay? Okay? It's the same thing with, let's say, a boy. Give him a nice haircut. Okay? And a girl, alright. They meet. Very good. And then what happens? They get married. Okay? But before they get married, there's this stage that you guys call the honeymoon phase. Okay? Honeymoon phase. Where you're calling every day, calling every day, good night every day, right? High energy, okay? Same thing with the chemical reaction. High energy. Hey, Shambile, have you passed? You know, same thing. And then after that, they get married. But remember, as we know, the honeymoon phase is high energy, but very unstable, and it's temporary. Same thing with the chemical reaction, okay? These reactants need to collide. This point of collision, where they have the most energy, is what we call the activated complex. Now, it's only at the point on top, right? This and this are not the same, right? It's only the point on top there, and the activated complex is there. The activation energy means from there to there. Okay? Now there's an important concept here that differentiates these two. Okay? Let's write that down again. Endothermic. Okay. Let's write this down here quickly. There's an important concept here called enthalpy. Enthalpy, and it's written as delta H. Okay? Now delta, we all know what delta is. It means a change in H, and this H actually stands for temperature, or energy actually. Right, so what do? We take the energy of the product, so we say delta H is equal to energy of the products, subtract by the energy of the reactants, okay? And what we're looking for is enthalpy positive or is enthalpy negative, okay? So we do the same thing here on this side. Energy of products, subtract energy of reactants. Okay. So what's happening here? What you're going to see is that the energy here is going to be negative. Right? And we see here the energy is going to be positive. Right? Because the energy of the because the energy of the products is there. The energy of the products is there. So if this is 0, then this is 1, and then that, let's make that 3. Right? The energy of the products is going to be higher, as you can see, than the energy of the reactants. Okay? Or reagents. Same thing. You're going to get a positive answer because this is higher than that. Here, you get a negative answer because the products there, okay, have a lower energy than the reactants. So the reactants have a higher energy, and they are the ones with the negative sign, so enthalpy is going to be negative there. So that's how we distinguish between an exothermic and an endothermic reaction. Is enthalpy for an exothermic reaction is negative, and an endothermic reaction is positive. Now what does that mean when you're doing a physical chemical reaction? This means when you're doing a physical chemical reaction, okay, when you're doing a physical chemical reaction, your reaction will actually give off energy, okay, energy to release a spark. It's like oxidizing magnesium. You have magnesium, there you go, plus oxygen, right, plus oxygen. When you add these two, right, they'll give you magnesium oxide, right? They'll give you magnesium oxide plus energy. will actually give off a bright spark. When you react with these with oxygen, they react and it gives you a bright spark and it gives off energy. Now an endothermic reaction takes energy from its environment, right? This gives off energy, this absorbs energy from the environment. So this reaction will be it's a warm reaction because it gives off energy. This one is a colder reaction, or let's say less warm, okay, than this one. So that takes energy from the environment. This gives energy to the environment, okay? So this is the difference between an endothermic reaction and an exothermic reaction. You look at the enthalpy. You look at products, you look at reactants, subtract the two, and then you get the difference. If it's negative, it's exothermic. If it's positive, it's endothermic, okay? All right. So that's the second energy graph that we're going to look at. Okay. Now, what we're going to look at, okay, is the catalyst. Okay, we're going to look at catalysts now. Let's write the mechanism of catalyst. Okay, mechanism of the catalyst. Okay, so let's define what a catalyst is, right? Catalyst is a chemical agent that speeds up a chemical reaction, okay, without changing the reaction. I'm saying it out just in case you don't see my handwriting. It's not the best. Okay, so how does it do this? So, to put this definition in more technical terms, right? What a catalyst does, so the function of a catalyst is to provide an alternate energy route, okay? This alternate route needs to have a lower activation energy. Okay, so what a catalyst does, it speeds up a chemical reaction. Now remember something very important, okay? So again, what we're going to do is that we're going to do the catalyst and then we're going to redo the energy graphs that we did previously, right? So the previous energy graphs that we looked at was the Boltzmann distribution curve. And then the second energy graphs are the potential energy graphs. Okay? Potential energy graphs in relation to the energy of the products and the energy of the reactants. Okay? We're going to do those again, but then what we're going to do is going to add the catalyst to those graphs and see how those graphs are going to change when we put a catalyst in them. Okay? So, important point. Catalysts do not cause reactions to occur. Writing this in bold because it's important. To occur. They only speed up reactions. Okay? So remember that, that's very important. Catalysts do not cause chemical reactions, they only speed them up. So you can't have a reaction, A plus B will give you C. Okay? Cannot have a chemical reaction, A plus B will give you C, at a lower activation energy than this reaction. Let's say the required is 24 degrees Celsius. And then you have this chemical reaction at 22 degrees Celsius. And then you think, oh, what I'll just do is I'll just add a catalyst. Let's put a catalyst like that, CO. Let's say CO is catalyst, right? You can't just say, I'll just add a catalyst and then the chemical reaction will start. That's not how it works. This reaction first has to be at this temperature. So it has to happen, okay? It has to start, okay, at 24 degrees Celsius, at that activation energy. Then when you add the catalyst, now I'm adding the catalyst, okay? Now what will happen? It will bring down the required energy of this reaction to 22. So it's not the other way around, okay? It first has to start, a specific chemical reaction needs to start at its original activation energy, and then the catalyst will drop the required energy to a lower energy, because that's its job. The function of a catalyst is to provide an alternative energy route. This alternative route needs to have a lower activation energy, okay? So from original, it drops it to low, but you can't take it from, I can't have a chemical reaction start below its activation energy, add a catalyst, and then cause it to react. It can only speed up a reaction that is already happening. Okay? Very important when it comes to the catalyst. Remember that. Okay? Right? Another quick comment. There are two types of catalysts. So two types of catalysts. So the first one is a homogeneous catalyst. Homogeneous catalyst. Okay? And then heterogeneous catalyst. Okay? Okay? What's the difference between the two? The first catalyst is in same phase as reactants, and this one is in different phase as reactants. Okay? Different phase as reactants. So there are two types, homogeneous catalyst and a heterogeneous catalyst. Okay? Now what we're going to do for our final part of the lesson, what we're going to do is going to take our previous energy graphs, which is the potential energy graph and the Boltzmann distribution curve. You're going to add the catalyst in there, and then you're going to see how the graphs are going to change due to the presence of the catalyst. Okay? Right. Let's quickly remove these. Okay. Alright, let's remove these. Okay, final part. So we're going to have again the Boltzmann distribution curve. Boltzmann curve. So this is distribution of kinetic energy basically. Okay, we're going to have a Boltzmann curve. Okay. All right. Okay. Let's make it a bit higher. Okay. We're going to have a Boltzmann curve over there. And then we're going to have the potential energy curves. That's what I call them. You can call them the enthalpy curves. You can call it whatever. Okay. Let's have an enthalpy curve over there. Okay. Remember Boltzmann curve. We talk about the activation energy. Again, let's call it E1. So the activation energy again is at E1 and beyond. Okay? Activation energy. Right? Activation energy. Okay? So we call this initial activation energy. Okay, so this is the initial activation energy. Okay, and these, what are these? These are particles that will collide effectively. So I'm speaking in terms of collision theory now. Particles that will collide effectively to form bonds. Okay, so I'm speaking now in terms of collision theory. So these particles have sufficient energy. Okay, again, these particles have sufficient energy to collide effectively and form chemical bonds. Bonds, what do I mean by bond? React. Right? These are the particles that will react. Right? Only at this temperature and beyond. Initial activation energy. This is the Boltzmann curve. And now we add a catalyst. Okay? We add a catalyst to the chemical reaction. Okay, let's write this down here. Number of particles. Okay, and the energy, again, energy, temperature, average kinetic energy. Okay, energy. Write that down. Okay, so now what we're going to do? Now remember this is energy, so it's increasing from 0 to that side. Okay, this is an increase in energy, plus. Okay, it's plus in this direction, right? And the amount of particles plus in this direction, upwards. Okay. Now what we're going to do is we add a catalyst to this reaction. Now, point I was speaking about, this reaction is already happening. So these particles are colliding effectively. They are already colliding at sufficient energy. So we're adding the catalyst while the chemical reaction is happening. Remember, see now when you add the catalyst, we're not starting the reaction. The reaction has already started. Okay? Now we add a catalyst. Add catalyst. Catalyst. Okay? We add a catalyst. Let's call this catalyst CO, right? We add the catalyst. What happens? Remember the definition was the function of a catalyst to find an alternative route for the chemical reactions at a lower activation energy. So the activation energy decreases in this direction, right? And it increases in that direction. So what's going to happen? Now the initial let's call it plus 0 because of the catalyst. Right? Now what's going to happen? Now what's going to happen, you noticed, is that now all of these particles will collide effectively. More particles collide effectively. Remember, this is in the language of collision theory, meaning react. Again, react. So now when you add a catalyst, it's not only these chemical reactions, but what the catalyst does is it lowers, right, the energy root of the reaction to a lower activation energy. So this activation energy is lower. That 0 is energy plus 0. It comes from there. That's what I named the catalyst to be. Right? The catalyst. So this is, again, adding of catalyst. Okay? Adding of catalysts increases the amount of particles availability to collide for effective collisions. So it lowers the activation energy such that more particles can collide to form chemical reactions. Now quickly, let's do a final graph, which I call the potential energy graph, which is this one, or you can call it the enthalpy graph or curve. Okay, right, here we have potential energy, okay, goes like that, goes like that. Okay, now here we have reactants, we have products. Okay, and then we have activation energy. Activation energy. Activation energy. I'm just shortening it now. And then there we have activated complex. Okay? Activated complex. What is going to happen if we add a catalyst, right, to the reaction? What's going to happen if we add a catalyst to the reaction is that obviously what kind of reaction is this? This is the difference, right? It's going to say enthalpy. Enthalpy is positive, right? Enthalpy is positive there, obviously. So what kind of reaction is this? This is an endothermic reaction, right? Once we do that, now remember this is the activation energy. Now remember it lowers the activation energy. So now what's going to happen is this is how it's going to look like. Okay? This is how it's going to look like now. Right? It lowers the activation energy from there all the way down to there. Right? So if you add a catalyst to a reaction, it lowers the activation energy. So now that's what that graph looks like. Now it looks like that. This is with change in curve due to adding catalyst. Okay, so we added a catalyst. Now the graph requires a lower activation energy right there. Right? A lower activation energy. Initially before it was higher. It had a higher activation energy at this point. Okay? So everything drops, the activation energy is going to drop. Now it's at this point. before it was at that point. So that's what a catalyst does. A catalyst will simply find a lower activation energy route, right, than the initial reaction, and lower the activation energy such that the chemical reaction happens at a lower temperature. Again, it doesn't cause a reaction, it just speeds up a reaction that is already taking place. Okay, so today that will be the conclusion of the lesson. Quick recap at what we looked at today and what we understood today. What did we look at today? It's already on the board. We looked at catalysts, right, and how they affect reactions. We looked at energy graphs, potential, energy graphs, right, those that look like this and like that. We learned about endothermic reactions and we learned about exothermic reactions. We learned about the mechanism. I learned about the mechanism of catalysts, right? Here we learned about as well the Boltzmann curve, which basically explains the distribution of kinetic energy within a chemical reaction and tells us which particles will collide effectively and form chemical reactions and which ones will not. So once again, that is how we conclude the lesson for today. Next week what we're going to do is we're going to do questions that are based on last week's lesson, which we were talking about the effects or the factors that affect chemical reactions and those sorts of things. Go look at that if you need to again. Today, the things I just mentioned now. Next week, what you're going to do is you're going to do questions based on the lectures from last week and this week. Okay, thank you, grade 12s. Cheers.